Welcome to our discussion on Newton's method. Newton's method is basically a way that allows us to get progressively better estimates for a zero of a function. If you have some really messy function and you're trying to find its zeros, remember where it crosses the x-axis, and it's too difficult to actually find them algebraically, you can estimate them by using Newton's method, which involves taking derivatives. And we know that for most functions, when you take a derivative, it kind of simplifies things and makes it easier to then find a zero. You don't get the exact answer, you get something that's close-ish, and then it's a recursive method that allows you to kind of do it over and over and over again, each time getting a better and better guess. You get closer and closer to that zero. There are certain times where this doesn't work, but for the most part it's a pretty good method. Let's take a look at an example here. Suppose that a car dealer offers to sell you a car for 18 grand, or you can make $375 payments per month for 5 years, or 60 payments. You'd like to know what monthly interest rate the dealer is in effect charging you, based on these monthly payments. Now, in order to find that answer, you have to solve this very ugly looking equation. And you might be asking yourself, where the heck did that come from? Well, there's a general formula. The amount owed, basically, right, is the payment amount over the interest rate times 1 minus 1 plus the interest rate to the negative n power. We can plug in what we know and isolate I and kind of solve for I. So we have 18,000 equals 375 over the interest rate that we don't know, 1 minus 1 plus the interest rate that we don't know, to the negative 60. Right? Okay, first thing I want to do is get rid of this parentheses, right? So I'm going to multiply both sides by I over 370, basically the reciprocal of this piece, to get rid of it. So now I'm going to have 18,000 I over 375 is going to equal 1 minus 1 plus I to the negative 60. Of course, we can clean this up, and this is just going to be, if you do the math, it's just 48I, because that's 18,000 divided by 375. So now we have 48I equals 1 minus 1 plus I to the negative 60. That's a plus I. We don't like this negative exponent. It really is 1 over this to the 60th power. So if we multiply everything through by 1 plus I to the 60th power, it'll get rid of that. So we get 48I times 1 plus I to the 60th, right, equals, well, 1 plus I to the 60th, because that's 1 times it, and then minus 1, because when you multiply this by itself to the 60th, right, the rule of exponent is you combine 60 minus 60 gives you 0. Anything to the 0 is just 1. And then if you bring everything over to one side, 48I 1 plus I to the 60th minus 1 plus I to the 60th plus 1 equals 0, and you can see that that's the same equation they have. So that's where it comes from. It basically comes from a compound interest formula where you're solving for I given the other bits and pieces. Okay, if we use some sort of graphing calculator or computer software, after zooming in and experimenting, we can come up with a graph that looks something like this, and zooming in further, you can see that that 0 is right there, which is somewhere between 0.007 and 0.008. And in fact, if you zoom in even more, you can get an approximate answer of that. And in fact, depending on if you're using a TI calculator or something, you can get a pretty accurate solution just right out of technology. So a faster alternative is to actually let the calculator do it for you, and that's where we get this number. So as with some other, not all, but some other calc techniques, you might be asking yourself, then why bother? Well, it's really more helpful when you start working in other dimensions and a higher order of things. So we're really just using this as a learning tool to be used later. It's a nice exercise in analytical thinking and being able to work through a problem, but for the most part, Newton's method is not something you're going to use on a regular basis. At least not for finding zeros of some functions, because you can just use computer software to do that. Okay, geometrically or graphically, this is what's happening. There's your blue function. You're trying to find that root, that r, that 0, at little lowercase r. So you guess this x1 value. And x1 gives you this actual value. Instead of 0, it gives you f of x1. Well, if you calculate the slope of the tangent line at that value and then figure out the equation of that tangent line, which is pretty easy to do, right? Then you can find where that crosses the x-axis, because then it's just a straight line, and figuring out where a straight line crosses is very simple. You set y equals mx plus b, right? You set that equal to 0 and solve. Very simple. So you can see that if x1 was your guess and then you calculated the tangent line at that point and then calculated where the tangent line crossed, can you see how that's a better guess than x1? And then we can repeat the process. We can now go up here, get this point, do the tangent line at that point, which will cross maybe somewhere around there, and there's my x3, and then do it over again, do it over, and it'll approach r. And that's what we're talking about here, is that if we want to find that estimate, we calculate the derivative at x1, right? So we're calculating the derivative at this point. We take that derivative, we evaluate it at x1, that gives us our slope. So now this is y minus y1 times, right, m times x minus x1. This is just the equation of the straight line that goes through this point. Once we have this equation, we set it equal to 0 and solve. So that's what we did here. We set y equal to 0 and solve, right? See, all that happened is y is now equal to 0. Well, if your derivative doesn't equal 0, which it shouldn't, because if your derivative equals 0 at that point, then that means you have a horizontal, right, slope, and then it will never hit the x-axis, unless of course it is the x-axis. So as long as we assume it's not 0, we can go ahead and do the division and solve for x2, right? All that's changing now is instead of, we're just talking about x minus x1, if we let it equal 0, if we let y equal 0, then that arbitrary x becomes x2. And then we just solve for x2. So we can see that if you divide both sides by the derivative, that's how we get this piece, and it's a negative, right? And then we add x1 to the other side, That's where that comes from. And then x2 is left all by itself, and they just swapped it and put x2 on the left. So we use this approximation, right, whatever x2 is, which is defined this way, as our next guess, and then we repeat the process. You can see that x2 is defined in terms of x1, and then x3 is going to be defined in terms of x2, and it's just going to repeat that process. So here's how x3 looks, right? And then there's the picture down below with a much prettier version of lines than the one I did on the earlier slide. Okay, so in general, each new approximation will spawn another one. And if those numbers get closer and closer to r as n gets larger and larger, meaning as we're taking the 6th, the 7th, the 8th, right, keep going on, then we say the sequence converges to r, and we can say that the limit of our xn's ends up equaling r. All right, let's look at an example. So we're going to apply Newton's method to the function x cubed minus 2x minus 5 and try and find the root of when it's equal to 0. We take the derivative is 3x squared minus 2, and then we're going to choose a starting point. Now, in order for Newton's method to work, you have to choose a starting point that's relatively close. So you would want to kind of graph the original function and get an idea of what would be your first best guess, because if your first best guess is just way off, sometimes Newton's method doesn't actually converge to that root. So just keep that in mind. You do want to come up with a good initial guess. So upon investigation, we can see that 2 is a pretty good guess. In fact, if you plug 2 into this function, right, into the original function, f of 2 is going to be 8 minus 4 minus 5, which is negative 1. That's pretty close to 0. So 2 is a pretty decent guess, right? And f of 1 we can see is even worse. So f of 3 being 16 is way worse. So this is really our best guess as far as simple values, right? You just want to start with a nice simple x, 1, 2, or 3. 2 ends up being a simple number that gets us somewhere close to 0. Okay, so let's apply everything to our formula. Right, equation 2, which is the general equation, which says each new guess is equal to the previous guess minus the function evaluated at that number over the derivative evaluated at that number. So if we start with n equals 1, and remember the function is really just the one on top, and that's the derivative. So if we evaluate them both at our first number, then that's what x2 is going to be. So our first guess was 2, right? x1 was 2, that was our first guess. Plug all that in, x2 ends up being 2.1, a little bit bigger. Now we can try it again. x3 is going to be x2, and then the same thing, function over its derivative, now evaluated at x2, so that's evaluated at 2.1. And when you do all that in the calculator and subtract it from 2.1, you get 2.0946. And it turns out that that number is already accurate to 4 decimal places, which is pretty good to have 4 decimal places of accuracy with only 2 iterations of this. We only had to do it twice. Okay, so that's the other nice thing about Newton's method is it's a quadratic method, which means you gain multiple decimal places with each try. You don't just gain kind of one extra decimal place of accuracy. It goes up quadratically. Okay, let's look at a simple proof of that this works. So starting with x1 equals 2, let's find the third approximation, i.e. x3, to the root of the equation x squared minus 1 equals 0, which we know has the solution x equals 1, right? X squared minus 1 X squared minus 1 is a simple quadratic that's just been shifted down by 1. So we know it has the solutions, right, the zeros of 1 and negative 1. So we know what the answer should be. We're going to guess 2, right? We're going to start out here at 2. And then we're going to see how close we get to 1, which we know is the right answer, after 3 iterations of this. So here's our original function, here's our derivative. Remember the standard formula is that the new x, right, is equal to the old x minus the function evaluated at that number divided by the derivative evaluated at that number. Okay, so x1 is going to be our first guess of 2. x2 is going to be x1 minus the function evaluated at x1 all over the derivative evaluated at x1, which is 2 minus f of 2 over f prime of 2, which is 2 minus, well, f of 2 is 4 minus 1, right, is 3, and then f prime, 2 times 2 is 4, so we have 2 minus 3/4, which is 5/4. So that's x2, 1 1/4. Okay. x3, the next one, is going to be x2 minus f of 5/4 over f prime of 5/4, which equals 5/4, right, minus f of 5/4, well, that's 5/4 squared, so that's 25/16 minus 1 all over 5/4 times 2, which is 5/2. And this comes out to be 5/4 minus, on the top we have 25/16 minus 16/16, right? So 9/16 over 5/2, 5/4 minus 9/16 times 2/5, that becomes an 8, right? And then this is 5/4 minus 9 over 40. Well, 5/4 is the same thing as 50/40 minus 9 of them, right? It becomes 41/40, and you can already see that we're only 1/40 off from 1, right? Because 40 over 40 would be 1, and in fact, if you do 41 divided by 40 in your calculator, 1.025. So that's how big our error is after 2 iterations. I mean, it's the third approximation, but we really only had to do things twice because the first approximation was just our first guess. If we did this again, x to the 4th, and if you want to do this on your own, I would suggest you do it just to make sure you can get there. It ends up being, if you leave it as a fraction, 3281 over 3280. So now the error is 1 over 3280, right? Because if we took those away, that would be exactly 1 over 1. And in fact, if you do 3281 divided by 3280, you get 1.0003 0.04878. So our error is now in the fourth digit, right? It went from the second digit to the fourth, right? We were off here in the hundreds. Now we're tens, hundreds, thousands. We're down here at 10,000. So we're gaining 2 spots already. And that's the Newton's method, guys. It's not too difficult. It's just a lot of tedious math, right?